In the last video, we talked about the gravitational field due to a thin uniform spherical shell, and in this video we are going to discuss the gravitational field due to a uniform solid sphere. So, to consider the field due to a uniform solid sphere, the first thing we need to do is we need to draw a sphere like this, and I'll select the point at which I'll be considering the gravitational field. Let us call this point as point P, and let us take the distance from the center of this sphere as r, and we'll consider the mass of this whole sphere as m, and this I have already considered the distance r. So we know the gravitational field due to an elemental volume that will be considered like this like a thin spherical shell having thickness small dx. Yes. So this is the total mass, and the gravitational field due to a small mass element dm is given by gm by Now to find the total field, that is the field due to the whole sphere, we will just integrate this. And for a point that is outside the sphere, that is for the point P located at outside the sphere, we can take this g by r square outside the integral, and this becomes integration dm, and integration of the whole mass element over this whole volume becomes m, so that gives us gm by r square. So at a distance r, due to a uniform sphere, solid sphere, the gravitational field will be just like that due to a point of mass m located at this point. So up next we are going to consider the field at an internal point. Calculating the field at an internal point is quite different from this calculation. So this is the sphere here of mass m, and here is the elemental volume of thickness dx and radius x. So I can find its density as m by 4 by 3 pi a cube, where a is the total radius of this solid sphere, and at point P, that is at a distance r from the axis, we will be finding the gravitational field. So we know from the formula that the gravitational field's magnitude is given by, for the elemental mass dm, it is given by g dm by r square. So for this case, this gravitational field will be located in this direction, and the total field we can calculate as equal to integration g dm by r square. Again here we can take this g by r square outside this integral. We'll just do that. And here you see we have considered this elemental volume, and to consider the elemental mass we'll need to multiply that elemental volume by density, and that is done by dm equal to m by 4 by 3 pi a cube times 4 pi x square dx. So this 4 pi will be cancelled out, and it will be 3m x squared dx by a cube. So I'll take the integral here, g by r square 3m x squared dx by aq, and the integral will be from 0 to r, that is the distance of the point P. So we'll take this 3m by a cube outside. Integral of x squared becomes x cubed by 3, and the limit from 0 to r. So 3gm by r square a cube, r cube by 3, here 3 and 3 will be cancelled out, and r square, and here is r cube, so this becomes r. So gmr by a cube. So you see that the field inside the sphere, this varies linearly, this increases linearly with the distance from the center. So if we draw a graph of the field versus the distance, so this is the magnitude of the field here, and this is the distance. So we'll get a maximum around here, that is a radius. So since inside the radius the field increases linearly with as r, so we'll find the field increasing like this, and outside the sphere the expression of the field is this, so this will decrease like this, and at the maximum point the field becomes, just put a here, that is gm by a square. You may also put a here, that becomes gm by a square, so you will find this maximum. So I hope you understand the concept of gravitational field due to a uniform solid sphere at a point both outside the sphere and inside the sphere. And for more videos like this, stay tuned and have a nice day.